Our next presenter, Stefan Gilles, several approaches to mass memory management. Take it away.
All right, thank you. This is the last block of the conference. I'll get right into it. This talk is about mass memory management, that is hard drives for satellites. And the question that I'll be addressing is, how does data layout affect storage performance? And to care about the question, you have to presuppose that you care about storage performance. So suppose you've got a satellite, it's up in space, it's taking science data. You would like that to be on the ground, but unfortunately you probably aren't over a ground station. So you've got to store that information somewhere on your satellite for a bit. And because you didn't ask to put storage on your satellite, you didn't really want it there in the first place, so you want it to be transparent. And for that, you want it to perform very well. So the question is, how can you get that good performance by meddling with the low-level data layout, where exactly those bits and bytes go? And I'll be going over some examples from recent SwRI projects. This is not going to be an incredibly detailed talk. This will more be a series of high-level observations and interesting cases that we've seen. So here are some of the projects that I'm going to be using to demonstrate these. These are not comprehensive. These are not even a representative sample. These are just the projects that make the points I want to make. And then we have some examples of the board pictures on the right there. These are all collections of NAND flash memory on a board with an FPGA to control data coming in and out of the NAND flash. And that FPGA is itself controlled by flight software. But for each of these boards, the flight software doesn't actually control or doesn't actually observe the data that's being stored in the NAND flash. It operates only as a traffic controller to move the data in and out. And I will go through the relevant parts of these projects as they come up. The only thing I want to point out from this table is that overall throughput and storage requirements are increasing over time, which is not a novel concept. So I mentioned NAND flash. That is what we are using for storing all this information. We like NAND flash because it has high storage capacity and low power requirements, which is great for space, and that information will persist even without power applied. The specific devices that we're using use 4 kilobyte pages. Those are the read and write units. Erase is a little bit larger. It's in 512 kilobytes. These do not include their own error detection and correction. However, a little bit of space is added on for each page to allow us to implement our own EDAC scheme on top of that. So the organization, because I promised it would actually matter, each device is going to hold about 8 die. Each die holds a bunch of blocks. Each block holds a bunch of pages. Those pages are the 4 kilobyte read-write units, but erasure happens at a block level, one level up from that. And then what's really cool is that the die can actually act independently as long as certain conditions are met. And we'll get into that in a bit. There are 3 operations on this flash memory that we care about. If you've got data already on your flash, you can read it off. And that requires a bit of overhead to specify the address, and then the actual transfer portion, which is 1 to 200 microseconds, and that's copying data directly off the flash into wherever it needs to go, like a radio. That is where the actual copper coming in and out of the device is in use. Writing data to NAND flash is similar, except you actually have to have a burn-in period after the transfer, and that burn-in period is about twice as long as the transfer itself. Finally, because, again, this is NAND flash, you can't just write and then rewrite data. There has to be an erase operation in between each write. And the bar is actually misleading here. The erase operation is by far the longest operation, up to 3.5 milliseconds. But it's okay because the erase operation affects multiple pages at once, so it's not quite as big of a hit as you might think at first. And then the color coding that I've used for this, red operations, only one operation at a time can be happening on any particular device because the red operations use that data path in and out of the NAND flash. You can't somehow be transferring multiple bits of data over one piece of copper. The blue and yellow operations, however, only require the resources of 1 die, and there are 8 die in each NAND flash component. So the note is that some of these operations could be performed in parallel if you can guarantee that they're going to be on different die. And that's a big if, but hold that thought. I will come back to that in a bit. One last thing that happens with NAND flash is that it can go bad in space. There's radiation up there. Individual components can eventually get corrupted. And so we need to have a method for replacing blocks that have gone bad with blocks that we've kept in reserve to preserve the same overall storage size throughout the mission. We implement that as a second piece of memory that holds a lookup table. The lookup table maps if we know whether a block has been detected as bad or not, and includes a replacement address. So this is our general scheme for bad block replacement, and then there are many variations as to how this can be performed. Okay, so that's enough for the hardware of the NAND flash that we use to produce these boards. And what I will be putting forward as the base heritage mission for a lot of this work is MMS's M3, the Mass Memory Module. This was launched in 2015. By 2021, it had 50,000 hours in orbit, and we got a paper out of analyzing the performance of the memory, which was, on the whole, very good. No new bad blocks were detected, so we did not have to make use of that bad block mapping. And our EDAC scheme was able to correct single-bit errors and detect double-bit errors, and we only detected 3 uncorrectable errors. Everything else was correctable. So this was MMS M3. It was largely successful. And what was the flight software for that? Well, it was based on RTEMS. We used CFDP for transfer reliability, but we did have to modify the NASA library that we used a little bit because we had no underlying file system. Instead, a file was a pre-allocated collection of 8 blocks totaling about 4 megabytes, and this was heavily tied to the instrument cycle. So if somebody told you that a certain block had a bad bit in it, and you had a sufficiently fine needle, you could literally pinpoint where on the board that data was being stored. That was how tightly the files were tied to the physical layout of memory. We used device-level EDAC protection, single-bit correction, double-bit detection. And any bad block marking that would have happened had to be done entirely manually on the ground. So it was very, very low level, no file system at all. There was onboard processing for priority to determine which files were downlinked first. So the question I can ask from there is, what interesting cases did we encounter when building on this heritage? And so the first one I will call making full use of hardware. And this is where we revisit the idea that some flash actions can be performed in parallel if they are on different die. And the question is, what kind of restrictions do you have to put on your mission operations in order to satisfy that if statement? And then what do you get in the then clause? And the claim that I would like to make is that if your operations allow random access to that memory, then you cannot meet this if condition. If you are allowed to place data at arbitrary locations in memory, then you can easily arrange a pathological scenario in which any future record operation has to hit pieces of memory that are on the same die. You have completely filled up 7/8 of your memory. That last eighth is completely associated to one die, and so you are unable to continue to record data and meet this condition of continually hitting different die. And that's bad for worst case analysis, which is what we need to guarantee. So the solution to this problem is to remove the ability for random memory access. The downside is huge. Your memory becomes a straight FIFO. You have exactly one location that you can write new data to. You have exactly one location that you can delete old data at. So this is a very restrictive downside, but the upside is that you get very good throughput. And so let's see an example of what that increase in throughput looks like. Here's the table I had earlier on of a couple missions from SwRI, or a couple products from SwRI, and I've divided the total throughput by the total storage. So that last column is now sort of a measure of how much we're making each byte work for throughput, how often we would be cycling through it if we were just continually running at fully supported throughput. And one of those numbers is a lot larger than the others. but if it's just written out in scientific notation like this, it's not quite visible. So here it is as a visual representation. That top bar, the one for FMC number 1, is more than 250% as throughput per storage as its closest competitor. So this obviously stemmed from interesting requirements, but that also means that we had to use interesting techniques to meet those requirements. So how did we get such a high throughput per storage ratio? Well, we partitioned the memory into 3 circular buffers. The 3 was how many different types of data you could store that came from instruments. So multiple instruments could record simultaneously, but we were able to very tightly predict the next memory address that was being used. And of course, the next memory address that would be deleted. So here's a visualization of a write procedure that is writing through a simplified picture of a die, and the red square that's moving through the memory is the pointer for the write address. So you can see there's die at the top and page at the bottom. This is a very simplified version of one block. And we are writing data repeatedly to each successive memory cell until we fill out the entire block. So red, following the color convention from earlier, is transferring data. We are putting data onto the die, or onto the device. We then have to perform a blue operation afterwards because we need to burn in that data. And then every now and then you'll see entire die go yellow. That's us pre-erasing the corresponding next block, so that by the time this write pointer finishes its traversal through this block, we are arriving at a fresh erased portion of memory to write into. So I call this strategy naive because it is not taking advantage of any die-based parallelism, but it's lucky because the order that the pointer is moving through memory is one that would allow for such parallelism if we had implemented it. So this is the naive picture, and then this is what it looks like when you actually apply that die-based parallelism. And this is the optimization that we used roughly on FMC number 1. And you can see that the same criteria are being met that are necessary for operating these devices. Only one red square is active at a time. Red is always followed by blue. No die is ever doing 2 things at once, and we are getting a total of 8 yellow operations by the time the right pointer makes its way through the full block. However, we're getting vastly superior throughput on the right side because we are running multiple operations at the same time. So the conclusion for this is that if your mission operations can handle the significant restrictions, then you can get a lot of advanced throughput by being very particular with how you lay out the individual bits and bytes of your scientific observations. Okay, so that's case 1. Case 2, we actually saw a bit about on Tuesday. This is the Cygnus mission. And the goal for the Cygnus mission, from the perspective of storage, was low-cost, low-volume microsatellites. So we want to downlink mission data with very limited resources. And how did we go about this? Well, again, no file system. We've divided the memory this time into 5 circular buffers, familiar, organized by data type, so that different instruments could put them in logically distinct portions. And each buffer was equipped with a record and playback pointer. And the interface exposed to flight software and to the ground was incredibly restrictive. You could do essentially 2 things. You could record X units of data to a particular buffer and then advance its record pointer. Or you could play back a buffer until the playback pointer caught up with the record pointer. Those were the only things you could do. You could not request to play back a certain size of data. You could just play back everything that hasn't been played back yet. It was incredibly restrictive. And we did some interesting storage tricks as well. We partially computed the CCSDS wrapping for the data as it went into NAND flash, which allowed very simple framing when it was being sent out to the radio. It could be implemented completely in hardware. However, as we saw on Tuesday, Cygnus was quite successful. It even got to be reused for alternate mission ideas after it achieved its purpose. So I would call it an unqualified success. And the conclusion to take away from it is that even if you have very limited resources, you can get your scientific data down onto the ground. Okay, So those two cases have been showing sort of very simple, stripped down low file systems or lack of file systems completely. What if we take things to the other extreme? So this is case 3, where the goal is to integrate with familiar and mature software. This is the high-performance single-board computer, and it has unusually low storage and no real throughput requirements because it's not managing scientific data. It's managing configuration for other mission components. So this device is not used as frequently as a scientific recorder. It just occasionally applies configurations and updates to other components of the satellite. It did use our standard NAND flash components, though, so we used the same technology for it. So since we did not have tight throughput requirements and we didn't need to apply the strange worst-case analysis to individually lay out the bits and bytes in memory, we were able to write device drivers for Linux and then deploy a pretty standard Linux kernel. I think it was 5.x something, just running our device drivers. And then on top of that, we put UBIFS, which is not quite a desktop class file system in terms of ubiquity, but it is much closer than a circular buffer. You can find it on flash drives and things. And so by writing a few device drivers that would marry our NAND flash to the Linux kernel, we were able to provide an interface to this NAND flash in normal POSIX operations, read, write, open, close. And UBIFS was very kind enough to provide its own bad block handling and wear level tracking. We did not need to handle any of that in our device drivers. But UBIFS was extremely configurable. We did not use its native error detection and correction. Instead, we used the standard error detection and correction that we put on these NAND flash devices. So we were able to tweak UBIFS very easily to meet our needs for that. And then the picture on the right is what we were able to provide to the client. We had to construct the parts in red. The parts in yellow were well-known, already existent objects that we used. And so when the client wrote their user flight software in blue, they were able to interact with the well-known, familiar yellow pieces of GNU Linux instead of with our custom FPGA drivers. So the conclusion for this is that if your mission allows you, you can have a very nice flight software environment that interacts with the comfortable software, GNU and Linux that you're already familiar with. Okay, now depending on where in the hardware-software camp you fall, you may be thinking, gosh, in this talk, all the cool stuff is on FPGAs. And you might be right. So here's an example in which flight software starts stepping up and playing a larger role along with the FPGA. So for these, the examples I'm going to use are the M4 missions. In this case, the mission mass memory, the M3, went through some more iterations and design expansion. So it became the multi-mission mass memory, and the number of M's increased by 1. These, in the first slide, I presented a couple of products. These are the ones with the highest storage, and they also have the highest complexity. They need to do simultaneous input and output on multiple logical channels and also multiple physical channels. So within the NAND flash devices, data is being accessed at multiple different locations simultaneously. In addition, as I'll talk about in a bit, we had a radiation mitigation strategy that involved specifying memory layout completely. This is all way too complicated to stick on an FPGA. So we had to draw a line in the sand of where that complexity would be divided up between the hardware, the FPGA controlling the NAND flash, and the flight software. And we chose to put the line in the sand at the block level. So from the FPGA perspective, it is responsible for handling how data flows in and out of any particular block of NAND flash. That means it has the opportunity to optimize page level access, those 4 kilobyte level pages. But the flight software is responsible for laying out files on the memory at the block level. So the where level information, that's all flight software. The actual the actual file level layout is pretty granular at the block address level, but that is all hidden from the FPGA. The FPGA is only aware of the fact that it is either recording or playing back over a specific logical channel, and those channels know which block they are operating now, which block they are operating on now, and which one they will operate on next. So the interface between flight software and the FPGA was a queue of which block do you touch next. And the FPGA was allowed to send an interrupt signal requesting more information in that queue, and it was flight software's responsibility to collect all sorts of information about wear level, file layout, whether the ground had requested seek or replay of certain files, and it was responsible for filling up that queue in order to keep the FPGA's tight timing requirements happy. And the FPGA was able to then apply all kinds of fancy optimizations to page-level read and write performance that I'm not even going to mention, but they could easily be a talk in themselves. Okay, so that seems to be a fairly decent division of labor between flight software and FPGA. What happened from that? Well, during the mission that M4 number 1 was used for, we actually started observing single event functional interrupts, SwRIs, during the mission. And those had a couple different symptoms. The first main symptom was that you would suddenly observe many multi-bit errors that EDAC claimed not to be able to correct, isolated to one individual flash block. But alternately, you could suddenly trigger the bad block detection isolated to one particular die. So these are all very bad things, but they're single event. And once power cycle was applied, both types actually vanished. So I believe the ultimate conclusion was that radiation was not actually destroying the NAND flash itself. It was affecting the circuitry that was controlling it and causing false positives on some of these detections. However, because block-level file layout was managed by flight software, we were able to reconfigure flight software to do some mitigation strategies that would reduce these SwRIs or prevent them entirely. The first mitigation that we applied was minimizing the time between erasing and writing. We call this just-in-time erasure. So this is NAND flash. You can't immediately write data and then write over it. You have to perform an erase operation between. That's why the erase operation is in there. And erase operations are actually when bad blocks are typically detected and noted and added to that table. But that means that after a block has been erased, when it's waiting to be written to, that's a vulnerable state. We do not want it to acquire SwRI errors in that time. So to minimize the time a block spends in that vulnerable state, we adjusted the flight software erasure scheduling. Second, since power cycling fixed these SwRIs, we wanted to build into flight software regular power cycling of different segments of memory. So if a segment of memory was not being touched, we would power it down and then power it back up when it was about to be used to clear out any accumulated SwRIs. However, we then run into file fragmentation in space. If you have a file and the blocks that it uses are scattered across all different segments of memory, including some that are powered down at any given time, then you will never actually be able to read your full file. So it's useful for flight software to apply a defragmentation strategy and try to isolate all blocks used in a particular file to one particular segment of memory. And again, because this was handled by flight software, we were able to update it after these SwRIs started to be detected and actually use that as a legitimate mitigation strategy to prevent these from interfering with operations. So the conclusion for this is that if you draw the right line in the sand and put complexity on the correct side, you can allow both components to do their heavy lifting. The FPGA is performing all those strange low-level optimizations that I talked about at the page level, getting really fast throughput in and out. But flight software, operating at a pretty granular block level for file layout, is also able to apply its own special logic and meet the mission requirements. So that's the conclusion from this case. And the overall conclusion that I'd like to take away from all of these examples are that you want to know your mission requirements, so you know what weird restrictions you can impose on your mission that it will accept. And you also want to know your hardware, including the low-level NAND flash, so that you can take advantage of those weird restrictions and gain better throughput and make better use of the money that you're paying for your satellite. And so now I will take questions with the caveat that a lot of this information does not originate with me, but with my coworkers, so I may have to defer a couple questions. Thank you.
Question online. How hard would it be to port the approach to other file systems other than UBIFS?
Right. I know that UBIFS is not the only file system we have looked at. I know that UBIFS was especially attractive for this operation because of that high configurability. We really wanted the ability to impose our EDAC scheme on it. We wanted the ability to be able to really provide it a blank, unstructured map of memory and have it make best use of it. But I know that there are other file systems, such as YAFS, yet another file system, that can be used in this situation. I would estimate at, say, very hard the ability to try and put, say, EXTFS or ZFS or HammerFS on this.
So what do you do to ensure the integrity of the bad block of memory?
Oh, so we use especially high quality MRAM for that. We try to keep the bad block table as small as possible because it's very expensive to make sure that it has all the redundancy needed to be the linchpin of bad block markings. So there's a lot of work that goes into minimizing the data that gets put in that small amount of MRAM, and that will be what will hold the critical segment.
We are over time, but I'm going to take one more question and close. Thanks.
Were the Cepheids confined to a specific radiation environment, and was there a significant loss of scientific data?
I believe the answer to the first is yes, although I don't have the full details on what that radiation environment was. But I don't believe there was significant loss of scientific data, especially once the mitigations were in play. This was a more complicated flight software setup in the first place, so it didn't have, say, Cygnus's downlink strategy of you only see it once. So there was the ability to power off a segment of memory, power it back on, replay the data, and observe that it no longer had those errors.
Thank you. There are more questions online. Please follow up with them on the slide.
All right. Thank you.